Hey there, it's Shannon Matchick-Myers, and today we're going to be looking at inner product spaces. This is a very cool section. A lot of you have probably experienced inner product spaces when you were learning about the dot product. That's actually the Euclidean inner product space. So let's learn about that and more. Are you ready? Awesomely awesome. Let's start out by just drawing a vector. Any old vector, call it V. And this vector V has the terminal point V1, V2. Good so far? All right, so looking at our picture here, this would have to be V1, correct? And then over here, this would be about V2. So if we drop this altitude here, it'll make a right angle with the x-axis, and this length will be beautiful, V2 minus 0, which is V2. And then what about the other length that we have going on? So this length here would just be V1 minus 0, which is V1. Groovy? Now, as we know from the Pythagorean theorem, if we take a look at the measure of this length, we can find it how? Well, if we call this the magnitude of V, it can be called length, magnitude, many different ways people talk about it. So the magnitude of V squared would equal to what? Well, we'd have V1 squared plus V2 squared. Good so far? And the magnitude is indeed a length. And so we would just choose the positive root. So the magnitude of V would be the square root of the sum of the squares of the other sides of the triangle. Cool so far? All right. So now let's look at the official definition of length of a vector in Rn. We will start with this. The length, norm, or magnitude of a vector, these all mean the same thing. V equal to V1, V2, all the way down to Vn. In Rn is given by the magnitude of V is equal to the square root of V1 squared plus V2 squared plus dot 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 plus Vn squared. Groovy? All right. So what do you think? When would the length of a vector equal to 0? Awesome. When your vector V equals the 0 vector. So let's look at this first example. We want to find the magnitude of U and the magnitude of V. So here we go. I'll show some more work when we're first starting it, but then I'll show less steps. I don't want you to be bored. So here we go. The magnitude of U is going to equal to, so my V1 would be 1. Well, it would actually be U1. So this would be like my U1 and U2, right? So we'd have the square root of 1 squared plus a half squared. And that's going to equal to, our magnitude of U will equal to 1 plus a quarter, which is 5 quarters, so we would end up with the square root of 5 over 2 units. Cool, cool? All right, what about the magnitude of V? V was equal to the vector terminating at 2, negative a half. So the magnitude of V will equal to the square root of 2 squared plus negative a half squared. So the magnitude of V is going to be 4 plus a quarter. So we would have what? Beautiful. Root 17 halves once we simplify, and that's in linear units. Next up, okay, let's explore. What's the magnitude of u plus the magnitude of v? Well, the magnitude of u plus the magnitude of v is equal to root 5 over 2 plus root 17 over 2, which would just be what? We can bring out the 1/2, write it a little prettier, and we would get root 5 plus root 17. And just for fun, if you take your calculator, hopefully you've got your calculator with you, if you find the decimal for this, we would have an approximate result of 3.18 units. Cool so far? So this is the exact, and then this one is the approximate. All right, well, you probably see where I'm going with this. Now, what if we sum the vectors first? So the magnitude of u plus v, remember what those were. We might as well plug that in. U was 1/1/2. And then v was 2 -1/2. All right, well, what's that going to give us? We're going to have the magnitude of the vector that terminates at 3, 0, which is equal to the square root of 3 squared plus 0 squared, which is just going to give us 3. And 3, notice, is not equal to 3.18. Cool? So you can't break apart the magnitude because you'd be breaking apart a square root, which we don't do. All right, very good. All right, now 3 times the vector u, we want to find that magnitude. Well, that would end up being 3 times the vector u, which is the vector that it terminates at 3, 3/2. And then this magnitude would be the square root of 3 squared plus 3/2 squared, which will be what? 9 plus 9/4. So we'd have, when simplified, good, 3/2 root 5. Cool so far? But isn't that, and that's in units, but couldn't we write this as (3/2 root 5 is equal to 3 times root 5 over 2, right? Which is 3 times the magnitude of u. So maybe there's some relationship there, right? Okay, well, let's see what happens. All right, well, if we multiply 3 times the magnitude of u, what are we going to get? We just did it up there. That would be 3 times 3/2. No. 3 times root 5 over 2, which is 3/2 root 5 units. And so what we found out was, what? 3 times the magnitude of u was equal to the magnitude of 3 times u. But what if that scalar had been a negative? What do you think? Well, it ended up being squared, right, in the radical. And so the principal square root of a number is what? Beautiful. The absolute value of that number. That's if you have a constant. So maybe it's really so the magnitude of 3 times u, maybe it's really the absolute value of 3 times the magnitude of u. I bet that's the case. All right. Okay. So, and then what did we also notice? That's one observation. We also noticed a big no-no. The magnitude of u plus v is not equal to the magnitude of u plus the magnitude of v. Okay? All right, so we come to theorem 4.1, length of a scalar multiple. Let v be a vector in Rn, and let c be a scalar. Then, the magnitude of c times v is equal to the absolute value of c times the magnitude of v, where this notation here is the absolute value of c. Well, let's look at the proof of that one. If we let v equal to v1, v2, all the way down to vn, so we're just writing it in component form, such that vi belongs to the real numbers for I equal to 1, 2, ... all the way down to n. Let's look at the magnitude of c times v. Well, when I write v in component form, it would be c times v1, v2, all the way down to vn. But don't I know that this is equivalent to the magnitude of CV1, CV2, all the way down to CVN? Well, what do I know about the magnitude? It's equivalent to the square root of all these components squared. So we have CV1, the quantity squared, plus CV2, the quantity squared, all the way down to CVN, the quantity squared. But look what happens. We get the square root of c squared v1 squared plus c squared v2 squared, all the way down to c squared vn squared. And what should we do with the c squareds? Beautiful. We can factor them out. So we'd end up with c squared times v1 squared plus v2 squared, all the way down to vn squared. And now what? Well, this will be equal to the absolute value of c times the square root of v1 squared plus v2 squared plus ... all the way down to plus vn squared. But what is that? Beautiful. That's equal to the magnitude of v. And so we've done our proof. Cool, cool? All right. So let's look at our next theorem. Unit vector in the direction of v. If v is a non-zero vector in Rn, then the vector u equal to v divided by the magnitude of v has length 1 and has the same direction as v. So this is really cool, and we'll be using this a lot. All right. So the proof for this is we know, and this is the reason it'll work. We know that v is not equal to the zero vector. So the magnitude of v is not equal to 0. And from that it follows that what? Beautiful. We can divide by the magnitude of v or multiply by 1 over the magnitude of v. So we've got it set up for part of our proof. It's defined and positive. Cool, cool? All right, so we also know that 1 over the magnitude of v is a scalar, and we've already said that it's non-zero, and it's okay to multiply by it, and it'll be positive. Cool so far? All right, so we'll have u is equal to 1 over the magnitude of v times v. So u has what? Good, it has the same direction already. Because it's 1 over the magnitude of v is just a scalar. And any scalar of v will have the same direction. And that was part of our proof. All right, well, if we know that u is equal to 1 over the magnitude of v times v, what could we do here? Good, we could look at the magnitudes. I mean, if these vectors are equal, right, then we need to fix it where the magnitude is equal, right? So let's see what we get. So this will give us that the magnitude of u is equal to, good, the absolute value of 1 over the magnitude of v, because that's a scalar, times the magnitude of v, right? Well, what's that going to be? The absolute value of a positive is just that quantity. So 1 over the magnitude of v times the magnitude of v. Okay, but the magnitude is just a scalar, right? So can't we divide these out to be 1? So the magnitude of u is just going to equal to 1. So u has length 1. 1. So we've shown what needs to be shown. Groovy? All right. Example 2. Find the vector v with a magnitude of 3 in the same direction as u equals 0, 2, 1, negative 1. Okay? Well, what should we do? Maybe we should find the unit vector for u, because then we can multiply it to any number we want to give it what length we want, right? So we'll go ahead and do this. So the unit vector for u would be what? U divided by the magnitude of u, which equals 0, 2, 1, negative 1, divided by the square root of 0 squared plus 2 squared plus 1 squared plus negative 1 squared. Groovy? All right, well, what do we get then? Well, the unit vector u over magnitude of u is going to be what's under that root. So we'd have 0 plus 4 plus 1 plus 1. So we'd have root 6, right? So we'd have 1 over root 6 times the vector. Groovy? And then, if you want, you could say root 6 over 6. I don't care about rationalizing denominators, but it's up to you. But don't get too happy with this response, because what do we have to do? We have to find v now, and we find v by doing what? Beautiful. We wanted v to have a magnitude of 3, and so we would multiply our result from the last one. So we're doing 3 times this unit vector for u, and that's going to equal to 3 over root 6 times 0 to 1 negative 1, which is equal to what? So bringing it inside, we'd have 0, 6 over root 6, 3 over root 6, and negative 3 over root 6. Or if you rationalize these, what would we get? Good, you'd have 0, root 6 over 2, and negative root 6 over 2. Groovy? So that's our final result. All right, so now let's look at our next skill. The definition of distance between two vectors. So now instead of just drawing one vector, why don't we draw 2 vectors? So we'd have, some vector v, and we'll just show the picture, of course, in 2 dimensions. And then we can have this other vector u, and so we'll have u is equal to u1, u2. Cool so far? And what we want to do here is we want to figure out this distance. So we want to know the distance between these two, right? This distance. So this distance is going to end up being the magnitude of something, right? So we'll just kind of keep it handy. All right, we'll have our little magnitude symbols ready to go. We want to write this magnitude in terms of u and v. So let's see what happens. I mean, it's really kind of cool how this ends up playing out. If we go back and we kind of do these images, okay, of the vectors that we had. Like that. And then also, let's take a look. I mean, if we continue to extend this vector u out a bit, look what happens. You get this magnitude vector that is parallel and the same length. Cool, right? So what is this vector right here? I mean, this vector here is the mirror, right, of u, but it's going what way? Beautiful, the opposite direction, right? So right in here, this part right here would be negative u. So let's see what we have here. Remember that this one here was our vector v, right? And if you've ever seen pictures where people are adding vectors together, the resulting vector comes to the point where that last vector hits, right? That's where the resultant vector will terminate. So what do we have here? Well, this vector is actually v plus negative u. Cool so far? All right, well, let's take a look at what we've got going on. The magnitude of v minus u, because plus negative u is minus u, right? Well, that's going to equal to, if I factor out a negative 1, what will I have? I'll have, good, u minus v, and that's all in the magnitude. But this will be the absolute value of negative 1 times u minus v in magnitude. And then that's just going to be 1, so then we'll just have the magnitude of u minus v. And that's what we have here, the magnitude of u minus v. Groovy? All right, so let's get the official theorem. So it turns out that the distance between the vectors u and v, that's how we denote it, is equal to the magnitude of u minus v. All right, so let's work an example. Find the distance between u equal to 112 and v equal to negative 130. So the distance between u and v is the magnitude of u minus v, which is equal to the magnitude of 112 minus negative 130. And this will be the magnitude of the vector 2, negative 2, and 2. And let's do a little trick here to make it easy. Can I factor out a 2 from that? And I'll have 1, negative 1, 1. So for my magnitude, I'll get absolute value of 2 times the square root of 1 squared plus negative 1 squared plus 1 squared, which equals 2 root 3 units. Cool, cool? Okay, so now let's play around a little bit more. So kind of like before, let's say that we've got a couple of vectors. We can still have v look something like this. And then the vector u, give us a little, well, I don't want this to be, let's say the vector u looks like this. Cool so far? All right. We also know what? We know that if we connect these two, we know that this is the magnitude of u minus v from our last theorem. And we do know also what? That this is the magnitude of v here, the length for the v vector, and the length for the u vector is the magnitude of u. Cool, cool? And I purposely had it where we don't have a right angle. And now let's take a look and let's work at finding out a couple of things. So we're going to look at finding out the angle between these vectors u and v. So to come up with our next idea, we need to look at the law of cosines. So let's see what we've got. I'm gonna make a triangle that looks something like what we have, somewhat of the look. And I'm going to call this angle C, so this would be side C. And then angle A, we have side A here. And then angle B gives us side B right here. Cool, cool? Okay, so what does the law of cosines tell us? Anybody remember? All right, just in case you forgot, this is what we know. We want to solve for C, right? So what we're going to do is use this form of it. So it's C squared is equal to the sum of the squares of the other sides, and this holds true for any of the sides that you isolate, by the way, except you, of course, switch stuff around a bit, minus 2 times the product of those sides times cosine of the angle opposite the side that you isolated. All right? So, let's look at it. We know that our side C is what? Beautiful. It's the magnitude of u minus v. And we need to square it, right? And that's equal to, so our side A would be what? The magnitude of v. Our side, now will be squared. And then our side B will be the magnitude of u. And that'll be squared. And then minus 2 times A times B, and you'll leave a space, I'll write them in, times cosine, and then the angle that we're interested in was what? Theta. Theta. And then we have magnitude of V for our A and magnitude of U for our B. Cool, cool? Okay, so let's do it. So, how would I work this out? What would the magnitude of U minus V be? If I square that out, what'll happen? Or don't worry about squaring it out. Let's just think about it. I mean, wasn't U equal to U1, U2, and V is equal to V1, V2. That's squared. And then I'm going to keep, and then so here, the magnitude of V squared is going to be what? Good. The square root's going to go away, right? And so I'll just have V1 squared plus V2 squared. And what about the magnitude of U squared? Awesome. U1 squared plus U2 squared. And then the other magnitudes I'm going to keep the same. So minus 2 magnitude of V, magnitude of U, cosine theta. Okay? Okay, so over here, I'm going to have this vector here, U1 minus V1, comma, U2 minus V2. And that's in magnitude. And then I still have this other stuff over here, V1 squared plus V2 squared plus U1 squared plus U2 squared minus 2 magnitude V, magnitude U, cosine theta. Groovy? All right, so now doing this magnitude, aren't I going to have U1 minus V1 squared plus U2 minus V2 squared? We all good with that? And then I still have all this other stuff. So V1 squared plus V2 squared plus U1 squared plus U2 squared minus 2 magnitude V, magnitude U, cosine theta. Cool, cool? Okay. So and you know what, let me put some so you can match up what's going on. So the magnitude of U squared was this here. And the magnitude of v squared was this quantity. And now we've got the, oh, and this should have been a square, sorry. So the magnitude of u minus v squared is this here. Cool, cool? Okay. So now let's expand it out. So we're going to have u1 squared, right? And then minus 2u1 v1 plus v1 squared. I'm just expanding out the square. And then plus u2 squared minus 2u2 v2 plus v2 squared. And that's equal to all this stuff we had. v1 squared plus v2 squared plus u1 squared plus u2 squared minus 2 times the magnitude of v times the magnitude of u cosine theta. All right? Just a little algebra, right? Okay, so just so you can keep track, this one here is this quantity, and then the other one squared out was this quantity. So let's see what we can cross out. This is the best part, right? Do you see that we have a v1 squared on either side, so we can cross them out. We have a u1 squared on either side, so those zero out. We have a u2 squared on the either side, so those zero out, and the v2 squared on the either side zeroes out. So that's a lot nicer, isn't it? So what we end up with here is negative 2 times quantity u1 v1 plus u2 v2. I just factored out a negative 2. And that is equal to negative 2 times the magnitude of v times the magnitude of u cosine theta. So the 2's divide out. So here we go. I'm going to go ahead and isolate cosine theta. All right? So we'll end up with cosine theta equals u1 v1 plus u2 v2 divided by the magnitude of v times the magnitude of u. Cool, cool? So this is very useful. And again, obviously you would apply the inverse cosine to both sides to find theta. But this is really cool because you learn a couple of things. This here, this quantity right here, happens to be the dot product, okay? The dot product of u and v. And so what is the dot product? Well, it's kind of a scalar of your cosine output, right? That's one way you could think about it, right? So keep that in mind. This is where the next two definitions come from. And hopefully working it out like that will help you remember it. So the dot product of u equal to u1, u2 down to un, and v equal to v1, v2 down to vn is the scalar quantity. So u dot v equals u1 v1 plus u2 v2, which is what we got in that numerator, plus dot dot dot, and you go all the way down to un times vn. Groovy? And the angle between two vectors is what? Well, the angle theta between two non-zero vectors in Rn is given by cosine theta equals, so the dot product, right? U dot v divided by the magnitude of v times the magnitude of u. Cool, cool? And then you have to think about, well, what can theta be bound between, right? I mean, you are dealing with a triangle, and a triangle is 180 degrees. In other words, pi, right? So here, 0 has to be less than or equal to theta, has to be less than or equal to pi. Cool, cool? All right, so why don't we go ahead and find the angle between u equal to 2, negative 1, 1, and v equal to 3, 0, 1. So let's write this formula so we remember it. Cosine theta will be u dot v over the magnitude of u times the magnitude of v. Keep your cosine theta going. A lot of times people forget to solve that at the end. So u dot v is going to be what? Well, 2 times 3 plus negative 1 times 0 plus 1 times 1 over the magnitude of u will be what? 4 plus 1 plus, that'd be root 6. And the magnitude of v will be root 10. Cool, cool? So, cosine theta will be equal to, we'll have what? 6 plus 0 plus 1, so that is 7, over root 60. And let's find that angle. I know root 60 can be simplified, but let's find this in radians, okay? So just in case you forgot how to do it, let's bring the calculator up. Make sure you're on radian mode. And I am. So what did we have? 7 over root 60. So we want to find what? The inverse cosine of 7 divided by root 60. And we'll get, when you do radian, you want to go 4 digits. So we get approximately 0.4425. I just evaluated the arc cosine of both sides. And we got that theta was approximately 0.4425. Nice thing about radians is you don't have to write that it's in radians. If there's no unit, it's assumed. Okay, so next up, example 5. Consider these vectors. So let's take a look at finding some properties about the dot product, all right? So let's find u dot v. U dot v will be what? Negative 1, 2 dot 2, negative 2. And that's going to equal to negative 1 times 2 plus 2 times negative 2. So that's going to give us negative 2 minus 4, which is negative 6. Groovy? Okay, what about v dot v? V dot v will be equal to 2, negative 2 dot 2, negative 2, which is the first component squared plus the second component squared. Doesn't that look familiar? Huh. If we square rooted that, wouldn't we have the length of the vector v, or the magnitude, right? So that's a groovy property. So this will end up being what? 4 plus 4 is 8. And the magnitude of u squared, so what was u again? Negative 1, 2. So let's take a look. That's going to equal to the square root of negative 1 squared plus 2 squared, so you can see it even better here, squared. So that'll just be Negative 1 squared is 1, so we'll end up with just 5. So the magnitude would have been root 5, but if you square it, what happens? Well, it's looking like u dot u is equal to the magnitude of u squared, right? From our last couple problems. Cool, cool. All right, so u dot v. So you have to kind of think about what you're getting. When you do a dot product, you get a scalar. And then if I multiply it to a vector, that scalar, I should get a vector, right? So didn't we find u dot v? Yes. U dot v was negative 6, and then the vector v is 2, negative 2. So this will be the vector negative 12, positive 12. All right, now how about u dot 5v? So let's see what happens. So we'll write it out a little bit more than you probably would have done. So this would be, what is it? Negative 1, 2 was our u, dot 5 times v, and v was what? 2, negative 2. Good. Okay, well, what happens with that 5? I mean, I could multiply the 5 into the v, right? I could multiply the 5 into the u, but I'm definitely not multiplying the 5 into both of them, right? So keep that in mind. This is going to end up being negative 1, 2, dot 10, negative 10, which will be negative 1 times 10 plus 2 times negative 10, which will be negative 10 minus 20, so we'll get negative 30. Okay, so here's our properties of the dot product. If u, v, and w are vectors in Rn and c is a scalar, then the following properties are true. U dot v is equal to v dot u. U dot the sum of v and w is u dot v plus u dot w. A scalar times u dot v is going to either be c times u dot v, or you could have it as u dot c times v. Okay? So the scalar only goes into one of the vectors. And what did we learn? V dot v is equivalent to the magnitude of that vector squared. And for 5, v dot v is greater than or equal to 0, and v dot v equals 0 if and only if v is the 0 vector. Okay? Okay. Example 6. Let's find this stuff using, you have to use properties of dot product to do it. So here we go. Here I've got 3u minus v dot u minus 3v. That's going to equal to what? 3u dot u minus what? 3u, actually I could say plus 3u dot negative 3v, and then bringing the v vector through, we'd have plus negative vector v dot u, and then plus negative vector v dot negative 3 times vector v. Cool, cool? Okay, well, this is going to be 3 times u dot u, right? So that's cool because we know that u dot u is 8. Now, here we go. We're going to have, well, we've got these two scalars, so why don't we call this one, we'll make this a negative, and we'll have minus 9 times u dot v, and then minus it's commutative, the dot product, so we'll have another u dot v, and then plus 3 times v dot v. Cool? Okay, so we know some of these things. Let's just clean it up one more little bit. 3 times u dot u, and then we'll have minus 10 of these u dot v's, and plus 3 v dot v's. So now plugging in the values that we know, u dot u is 8, so we'll have 3 times 8. U dot v is 7, so we'll have minus 10 times 7. And then v dot v is 6. So u dot u was 8. U dot v was 7. And v dot v was 6. And then when we clean that all up, we're going to end up getting negative 28. Okay, so here's a very famous theorem, the Cauchy-Schwarz inequality. So if u and v are vectors in Rn, then the absolute value of the dot product of u and v has to be less than or equal to the product of the magnitudes. Where this guy here, again, denotes absolute value of the dot product. Okay, so let's look at the proofs, okay? So this one we're going to have a couple of cases. Case 1, why don't we go ahead and we'll assume that u is the 0 vector. Okay? So then the dot product, the absolute value of the dot product between u and v, is going to end up being, if I have the 0 vector, so I have the dot product of the 0 vector and v. But what is that? That's going to be the absolute value of 0, which is 0. And that means that our magnitude, the magnitude of u times the magnitude of v, would be 0 times the magnitude of v. Remember, the magnitude of v is just a scalar, so that's going to be 0. Cool? Well, 0 is less than or equal to 0, so we're done with that part. Okay, case 2. We're going to have it where u does not equal to 0. So let u not be equal to the 0 vector. And we're going to let t belong to the real numbers. So what we're going to do with this one, if u is non-zero, right, and t belongs to the real numbers, then t is going to serve like as a scalar, right? So if I want to think about this sum here, t times u plus v. So what's going to happen? Well, if I look at the dot product of t times u plus v with itself, what's got to be true? It's got to be greater than or equal to 0, right? Now let's play this. Let's play with this a little bit more. So if I'm looking at this dot product, can't I use some properties? This would be what? T times u dot t times u plus t times u dot v plus v dot t times u plus v dot v. Cool so far? And we know that this has got to be greater than or equal to 0. All right. Well, let's keep going. What happens with this? I'm going to end up with t squared times u dot u. And then I'll have 2 of these t times u dot v's, right? And then I'll have plus a v dot v. And this has to be greater than or equal to 0. Okay. So, what does it look like here? I mean, isn't this quadratic in form? So, what if I let a equal to u dot u, b equal to u dot v, and c equal to v dot v? So I would have a times t squared, and then what? Plus 2 times b times t plus c, and that's going to be greater than or equal to 0. Okay, so this is parabolic in form, right? And if you have a parabola that's greater than or equal to 0, what has to be true? Beautiful. It's going to open upward, right? We know that a is positive and non-zero because a equals u dot u. And so let's write that in. Since a is greater than 0, the parabola opens upward. Now, think about a parabola opening upward and being greater than or equal to 0. So it's either what? Tangent to the x-axis, so it crosses it exactly 1 point, or it is what? It has imaginary roots, right? So if at squared plus 2bt plus c equals 0, we have that tangent situation. So it would be a single repeated root. Because remember, you'd end up having a degree of 2, so you'd have one root with multiplicity 2. If a times t squared plus 2bt plus c is greater than 0, we'd have what? No real roots. Groovy? Okay, so now let's see. Why don't we take a look at what our discriminant would be, right? So our b in this case is going to be the 2b, right? Because that's the coefficient to the t. So our discriminant would be two b squared minus 4 times a times c, and that's going to be what? If I know that it's either a single repeated root or no real roots, that means that you'd get a 0 or a negative in the discriminant for the quadratic formula, right? So it would be less than or equal to 0 with the combined knowledge those two give us. And so that would give us 4b squared minus 4ac is less than or equal to 0. And so 4b squared would be less than or equal to 4ac, the 4's divide out. And then what were our, our B and A and C? Let's put that back in. So our B was U dot V. So we'd have U dot V squared, and that would have to be less than or equal to, A was U dot U and C was V dot V. So U dot U times V dot V. Okay, but don't we know, this theorem has magnitude in there, right? And so here, wouldn't it be nice to put that in terms of the magnitude? So I'd have U dot V squared would be less than or equal to, beautiful, the magnitude of U squared times the magnitude of V squared. Cool? And we know that V is positive or 0. And so if we evaluated, think about evaluating the square root, we would end up getting the absolute value of U dot V is less than or equal to what? The magnitude of U times the magnitude of V. And we didn't have to go, you're not going to have intervals of it being negative because of that special, these cases that we have. Because we know that AT squared plus 2BT plus C is greater than or equal to 0. So we have less to worry about when we're doing the algebra here. Groovy? So that's the proof. I love that proof, don't you? So now let's just do a quick problem where we verify the Cauchy-Schwarz, sorry, I lost my Y here, inequality for U equal to -1, 0 and V equal to 1, 1. So, to verify, we have to show that the absolute value of U dot V is less than or equal to the magnitude of U times the magnitude of V. Okay? So, all right, let's see. What's the absolute value of U dot V? We would have -1 times 1 plus 0 times 1 inside that absolute value. And it would need to be less than or equal to, so the magnitude of U is going to be what? The square root of 1, right? And then the magnitude of V is going to be the square root of 2. So let's see what we get. This would be -1 plus 0 is -1. The absolute value of -1 is 1. And is this true that 1 is less than or equal to root 2? Yes. So it's verified. Cool? All right, so now let's look at orthogonal vectors. Two vectors U and V and Rn are orthogonal if. What do you think? Well, if their dot product is equal to what, do you think? Good. 0. Okay? So determine all vectors in R2 that are orthogonal to U equal to 3, 1. Well, why don't we let some vector V equal to V1, V2, right? So U dot V, and we set that equal to 0. So what's going to happen? We'd have 3, 1 dot V1, V2 equals 0. And so what would that give us? 3V1 plus V2 would have to equal to 0. That's the dot product. So isolating V1, we would get what? -1/3 V2. And then parameterizing this and putting it in a set, what would happen? We'd have -1/3 T, T, such that T belongs to the real numbers. Those are all the vectors in R2 that would be orthogonal to U. All right? Okay, so next step we have the triangle inequality, another famous inequality. So if u and v are vectors in Rn, then the magnitude of the sum of u and v has to be less than or equal to the magnitude of u plus the magnitude of v. All right? So we'll use our Cauchy-Schwarz theorem in here. So now, what should we do? Let's start off with the magnitude of the sum of u plus v squared. Right? And what do we know about that? We know that that equals to the dot product of their sum, right? Cool, cool. All right, now using those properties that we just learned for dot product, this is going to give us u dot u plus u dot v. I don't really need parentheses. Plus v dot u plus v dot v. Cool, cool? So this will be what? U dot u plus 2 of these u dot v's plus v dot v. Now that we've done a little simplification, why don't we go ahead and put this back in terms of magnitude? So this would be the magnitude of u squared plus 2 times u dot v, and then plus the magnitude of v squared. Groovy? Okay, so what we've done here is we've said, okay, these are equivalent. So now let's start our new thought. So the magnitude of u plus v squared has to be what by the Cauchy-Schwarz? What did Cauchy-Schwarz say? Remember? So the absolute value of the product of, so the absolute value of the dot product of two vectors has to be less than or equal to their product of their magnitudes, right? So let's see what we got. Why don't we go ahead and say that this is equal to the magnitude of u squared plus 2 times the absolute value of the dot product of u and v, so we can apply that theorem, plus the magnitude of v squared. Groovy? So now we'll apply our Cauchy-Schwarz, and this, was a less than or equal to. So magnitude of u plus v squared has to be less than or equal to the magnitude of u squared plus 2 times the magnitude of u times the magnitude of v. That's applying Cauchy-Schwarz. So going from here to here and utilizing the fact that we've got this inequality going on. Okay? Don't forget to add this guy. Cool, cool? All right, so now what do you think? Well, the magnitude of u plus v squared has to be less than or equal to, what would that be? Can you write that as a perfect square? I mean, isn't this the magnitude of u plus the magnitude of v, the quantity squared. Now we know that all of these are non-negative, right? So here, that's going to mean that the magnitude of u plus v would be less than or equal to the magnitude of u plus the magnitude of v. Cool, cool? And that they're non-negative. Okay. And we're done. We've shown it. Cool, cool? All right. So our next theorem is the Pythagorean theorem. So if u and v are vectors in Rn, then u and v are orthogonal if and only if the magnitude of u plus v squared equals the magnitude of u squared plus the magnitude of v squared. Cool, cool? So that's a new way of finding out if something is orthogonal. So let's verify the Pythagorean theorem for the vectors u equals 3, -2, and v equals 4, 6. So let's do it. The magnitude of u plus v, the quantity squared, equals magnitude of u squared plus the magnitude of v squared. And then we want to see if it's true. So the magnitude of u plus v, so u plus v would be what? The vector 7, 4. And we want to know, is that equal to, so what's the magnitude of u squared going to be? Good, 13. And then the magnitude of v squared will be, what is that, 16 plus 36, 52? Alrighty, so I'm just going to do, this is equivalent to 74.74. Is that equal to 65? So here, what would we get? 49 plus 16. Is that equal to 65? Yes, 65 equals 65. We've verified it. All right, so now we get to inner product. So you got to work with something that you're hopefully used to, or you'll soon be used to if you haven't taken Calculus 3 yet. And now, this is why I didn't want you to use the carets for vector notation before. That's because in linear land, it means inner product space, okay? So here we go. The inner product of u and v, all right, so u, v, and w are vectors in any vector space v, and c is a scalar. So an inner product on v is a function that associates some real number, which is the inner product of u and v, with each pair of vectors u and v, and satisfies these axioms. So if you want to know if something is an inner product, you would have to check these 4 axioms. So it turns out that the inner product of u and v is equal to the inner product of v and u, and the inner product of u and the sum of v plus w is equivalent to the inner product of u and v plus the inner product of u and w. A scalar times the inner product of u and v is equivalent to c times u within this inner product and v. And then for the inner product of v with itself being greater than or equal to 0, and the inner product of v in itself being equal to 0, this only happens what? When v is the 0 vector. So like I hinted to you, the dot product is the Euclidean inner product for Rn. Groovy, huh? All right, so example 8. Show that the function inner product of u and v equals u1 v1 plus 2u2 v2 plus u3 v3 defines an inner product on R3, where u equals u1, u2, u3, and v equals v1, v2, v3. So you have to just be open-minded, okay, because we're just defining a different inner product, okay, and we need to show that it works out. So we're also going to need, why don't we let W equal to W1, W2, and W3, all right? And so we're going to let UI, VI, WI belong to the real numbers for I equal 1, 2, and 3. We're also going to let C belong to the real numbers. Cool, cool? Okay, so here we go. First off, we are checking what? The inner product of u and v. We need to see if it's equal to the inner product of v and u. Okay? So let's do it. The inner product of u and v equals to, and we were given their inner product, so it's u1 v1 plus 2u2 v2 plus u3 v3, okay? Well, isn't that, the real numbers are commutative, right? So that would be v1 u1 plus 2 v2 u2 plus v3 u3, which equals to the inner product of v and u. So that one works. Cool, cool? All right, so again, remember, we're bringing this back to the real numbers, just like when we were first learning about vectors and matrices properties, right? Matrix properties. So you have to do this, all right? No shortcuts. All right, secondly, what did we need to know? We needed to look at if we had the inner product of u and the sum of v and w, and we need to show what? That would equal to the inner product of u and v plus the inner product of u and w. So let's check it out. Start with that left side, the inner product of u and v plus w. Be careful with your grouping symbols, okay? Is going to be what? Well, we'll have u1 and then what? Beautiful, times the sum v1 plus w1, and then plus 2u2 times the sum of v2 plus w2, and then what? Plus u3 times the sum of v3 and w3. Cool, cool? Okay, well, the real numbers are distributive under addition. So this is u1 v1 plus u1 w1 plus 2u2 v2 plus 2u2 w2 plus u3 v3 and then plus u3 w3. Groovy? Now, the real numbers are what? Commutative, right? So let's move them around. We've got u1v1 plus 2u2v2 plus u3v3, and then plus u1w1 plus 2u1w1, sorry, 2u2w2, and then plus u3w3. Groovy? But what is that? That's the inner product of u and v plus the inner product of u and w. Cool, cool? So that one's done. Just a few more, right? Actually, two more. So now we have to do the scalar business, right? So the inner product of, C times the inner product of u and v, and that's supposed to equal to the inner product of C times u and v. So let's check it out. C times the inner product of u and v is equal to C times u1v1 plus 2u2v2 plus u3v3. Well, this is equal to, the real numbers are distributive, right? So this will be C times quantity u1v1 plus C times the quantity 2u2v2, and then plus C times the quantity u3v3. Groovy? Okay, so now I want to do what? I want the C's to be with the U's, correct? Right? So I'm going to use the associative property on this. So what would I have? I'd have beautiful CU1 times V1 plus C times 2U2 times V2 plus CU3 times V3. Now the real numbers are commutative. I've got to move that 2, right? So I'll have CU1 times V1 plus 2 times CU2 times V2 plus CU3 times V3. And finally, this is the inner product of CU and V. Cool, cool. So that checks this guy off. So the fourth one that we have going on here is two-parter, right? Remember that the inner product of V with itself is greater than or equal to 0, and the inner product of V with itself equal to 0. How did it read? If and only if V was equal to the 0 vector. So let's take a look, okay? Well, what would V dot V be? That's one way to start her off. Or not dot V, sorry, the inner product of V with itself. So the way it's defined here, we would have V1 V1 plus 2 V2 V2 plus what? V3 V3. Cool, cool? What is that? V1 squared plus 2V2 squared plus V3 squared. Now, what do we know? All of these are being squared, right? So all of these have to be positive, right? So we know that the inner product of v with itself has to be greater than or equal to 0. Since all vi terms are squared. And terms are being summed cool. So that's one part of it. All right. Well, similarly, let's look at how could the inner product of v with itself be the 0 vector? Good. I mean, they'd all have to be 0, right? Because nothing's being subtracted out. So v, inner product of v with itself, must equal to 0 for v1 squared plus 2v2 squared plus v3 squared to be equal to 0. Groovy? All right, so we're done. We verified an inner product. Isn't that exciting? All right. So here, let's look at some examples of some real interesting inner products. Okay, so show that the function, the inner product of u and v equal to u1 v1 minus u2 v2 minus u3 v3 does not define an inner product on R3, where u equals u1, u2, and u3, and v equals v1, v2, and v3. You have to sort of think about what's going to fail, you know? So basically, in order for the inner product of a vector with itself to be 0 and greater than or equal to 0, has to be for that vector to be the 0 vector in order for it to be an inner product space. So here I see these minus signs, right? And so what if we let u equal to, I'm going to have one of the terms be 0. I want something like this. If we had 2, 2, 0. Where I'm headed with this is I'm looking at this difference here. So if the first and second components of a vector, are the same, that'll 0 out. And if the last component is 0, you'll end up with an inner product of 0, but this is clearly not the 0 vector, right? Do you see this is not the 0 vector? So let's check out the inner product of u with itself. So that'll end up being what? 2 times 2 minus 2 times 2 minus 0 times 0. Which is equal to, 0. But the fact that u is not the 0 vector violates it. So 2, 2, 0 is not equal to 0, 0, 0. So the fourth axiom doesn't hold true. Cool? Properties of inner products. Let u, v, and w be vectors in an inner product space V, and let C be any real number. So it turns out that the inner product of the 0 vector with some other vector V is equal to the inner product of V with the 0 vector, which is going to be equal to the scalar 0, right? And then you can go the other way that we went from, you saw a similar property in the axioms. This is going to be equal to the inner product of u and w plus the inner product of v and w. And to do the proof for this, well, let's just take take it from the left side, u plus v, inner product of u plus v and w, that's going to equal to, I know that we can commute them, right? So we'd have this equivalent statement, but didn't we already learn that this was equal to w, we use different vector names, but this will be equal to the inner product of w and u plus the inner product of w and v. Cool so far? But what do we know? We know we can commute them within the inner product, right? So this is going to be equivalent to u, inner product of u and w, plus the inner product of v and w. Cool? And then we have another property for a scalar. So if you have the inner product of a vector u and a scalar times a vector v, that's going to be equivalent to the scalar times the vector u and v, which is also equal to c times the inner product of u and v. Cool? All right. Now, these are all the same definitions. We're just using general inner product notation as we learned for the dot products. So, definition of length, distance, and angle. So the length or norm or magnitude of u is going to be magnitude of u is equal to the square root of the inner product of u with itself. The distance between two vectors u and v is distance between u and v equals to the magnitude of u minus v, just like before, but we could write that, couldn't we, as the square root of the inner product of u minus v with itself. The angle between two vectors u and v, what do you think that's going to be? Cosine theta equals the inner product of u and v divided by the magnitude of u times the magnitude of v. And then what was the condition on that angle? Beautiful. It's between 0 and pi inclusive. And then u and v are orthogonal when their inner product is 0. Cool? All right. If the magnitude of u equals 1, then u is called a unit vector. Moreover, if v is any non-zero vector in an inner product space v, the vector u equal to v over the magnitude of v is a unit vector and is called the unit vector in the direction of v. Now, inner product on the set of continuous functions on a closed interval from a to b is inner product of f and g is the integral from a to b of f at x times g at x with respect to x. Yes, you still have to know how to integrate. The inner product on all 2x2 matrices is denoted inner product of A and B, and that would end up being A11 B11 plus A12 B12 plus A21 2, 1 plus A, 2, 2, B, 2, 2. Groovy? The inner product on the set of polynomial functions is the inner product of P and Q. There should be a comma there, sorry. And you end up getting A0 times B0 plus A1 times B1 plus A2 times B2 plus ... plus AN times BN, where P equals A0 plus AX, A1X plus A2X squared plus ... plus ANX to the N, and Q would equal to B0 plus B1X plus B2X squared plus ... plus BNX to the N. Okay, so let's look at this inner product defined on Rn. So again, it's been defined, we're going to use it. All right, so here we go. Let's find this stuff using this inner product. Doesn't matter that it's not the dot product. Get that out of your brain. It's been defined for this problem. So u is 0, -6, and v is -1, 1. So what's the inner product of u and v? Well, u1, v1, so 0 times -1 plus 2 times u2, v2. Cool, cool? And that ends up giving us -12, the magnitude of u. So we have to use inner product because we're not using the Euclidean dot product, so you can't use the definitions that were based on the dot product, okay? So here we go. This is going to be the square root of the inner product, right? And actually, let me write that out. So this would be the square root of the inner product of u with itself, which in this case is the square root of, so inner product of u with itself, we would have 0 times 0 plus 2 times -6 times -6. And that in turn gives us a result of what? 6 root 2? Cool, cool? Okay. And of course, these are in units, right? That would be in units because it's a length. All right, the magnitude of v, again, is going to be the square root of the inner product of v with itself, which will be the square root of -1 times -1 plus 2 times 1 times 1. And that will be √3 units. Okay. Now the distance between u and v. So the distance between u and v will be equal to what? Beautiful. The magnitude of u minus v, which will be the magnitude. What's u minus v? It would be the vector -1, -7, and that will be the square root of -1 times -1 plus 2 times -7 times -7. And that'll give us 1 plus 98, right? So that would be 99, I think. So that would equal to, let's see, 9 times 11 is 99. So we'd have 3 √11 units. All right. Next up, let's take a look at the inner product for the set of continuous functions from -1 to 1. So here we go. This is going to be, so remember my a in this case is -1, my b is 1 from the integral, right? So the inner product of f and g is equal to the integral from -1 to 1 of f of x times g of x, so negative x times x squared minus x plus 2 with respect to x. That's going to give us the integral from -1 to 1 of what? Negative x cubed plus x squared minus 2x with respect to x. And then we'll have -1/4 x to the 4th plus 1/3 x cubed minus x squared evaluated from x is -1 to x is 1. So this will be what? Upper limit of integration, -1/4 plus 1/3 minus 1. Lower limit of integration, we got to be careful of. We'll have a -1/4, and then we will have a -1/3 this time, and minus 1. So what's going to happen? These will zero out, and what do we get? We'll get 2/3, -1 plus 1. They're going to zero out. So we just get 2/3. How'd you do? Awesome. Next up, the magnitude of f. So the magnitude of f is going to equal to what? The square root of the inner product of f with itself, right? And that in turn will be the integral from -1 to 1. Okay, so that's going to equal to, be careful, remember there's a square root around everything. So that's going to be the square root of the integral from -1 to 1 of -x times -x with respect to x. So that's going to be, what's that, x squared? So that'll be the square root of the integral from -1 to 1 of x squared dx. And that's going to be 1/3 x cubed from x is -1 to x is 1, which will be the square root of 1/3 times 1 minus -1, which will be the square root of 2/3. Or that one looks kind of mean. Why don't we rationalize the denominator to get √6 over 3. Cool, cool? All right, continuing the magnitude of g. So this one will be a little more mean, all right? Remember that the magnitude of g is going to be equal to the square root of the inner product of g with itself, which is going to be the square root of the integral from -1 to 1 of x squared minus x plus 2 times x squared minus x plus 2. So we'll have, once we combine everything, the integral from -1 to 1 of the quantity x to the 4th minus 2x cubed plus 5x squared minus 4x plus 4. And then integrating, we will have the square root of 1/5 x to the 5th minus 1/2 x to the 4th plus 5/3 x cubed minus 2x squared plus 4x. And that's going to be evaluated from x is -1 to x is 1. So we will have 1/5 minus 1/2 plus 5/3 minus 2 plus 4 for the upper limit, and then minus -1/5 minus 1/2 minus 5/3 minus 2 minus 4. And let's see if anything zeroes out. The 1/2 will zero out. The 2's will zero out. And I think that's it. So then we'll get the square root of, what's that going to be? 2/5 plus 10/3 plus 8. And once you simplify that a bit, we will get what? The square root of 176 over 15. It turns out if you rationalize that, you'll end up getting 4 root 165 over 15. Cool, cool? Right, now the distance between f and g. So here we go. That's going to equal to the magnitude of f minus g, which will be equal to, let's see what this looks like. The magnitude of f, remember, was what? -x, and then minus g, and g was what? X squared minus x plus 2. So that's going to be the magnitude of negative quantity x squared plus 2, which will be absolute -1 times the magnitude of x squared plus 2. And that's just the magnitude of x squared plus 2, which is the integral from -1 to 1 of x squared plus 2 times x squared plus 2 with respect to x. Hopefully, I forgot that up here, my bad. Good. All right, with respect to x, and that's going to give us what? The integral from -1 to 1 of x to the 4th plus 2 times x squared. Sorry, I'm getting tired. 2 times x squared times 2. So we'd have 4x squared plus 4 with respect to x. All right, so then let's see what we get. So this will be the square root of 1/5 x to the 5th plus 4/3 x cubed plus 4x, evaluated from x is -1 to x is 1. And we will have the square root of 1/5 plus 4/3 plus 4 minus -1/5 minus 4/3 minus 4. So that will be, nothing will zero out on that, I don't think. So that's going to be the square root of 2/5 plus 8/3 plus 8, which, with a little bit of arithmetic, will give us the square root of 166 over 15, Or if you want to rationalize it, it would be root 2,490 over 15 units. All right. Next up, we have another theorem. Let U and V be vectors in an inner product space V. And the Cauchy-Schwarz triangle and Pythagorean theorems, they all work, okay? So the Cauchy-Schwarz will now look like the absolute value of the inner product of U and V needs to be less than or equal to the product of their magnitudes. And the triangle inequality was what? The magnitude of U plus V is going to be less than or equal to the magnitude of U plus the magnitude of V. And the Pythagorean theorem, U and V are orthogonal if and only if the magnitude of U plus V squared equals the magnitude of U plus the magnitude of V. Cool, cool? Okay, so next up we're going to verify the triangle inequality for these matrices. So let's see if it works. We have that inner product there. That's the one we were given earlier. The magnitude of A plus B is that less than or equal to the magnitude of A plus the magnitude of B. All right, so here we go. On the left side, we're going to have the square root of the inner product of A plus B with itself, A plus B. And we want to see if that's less than or equal to the square root of the inner product of A with itself plus the square root of the inner product of B with itself. So let's do it. Let's see, what is our A plus B? If we just kind of come out here, A plus B would be what? The matrix 1, 2, 4, negative 3 with itself 1, 2, 4, negative 3. So that'll be on the left. And then on the right side, we'll have the magnitude of 0, 1, 2, negative 1 with itself. Plus the magnitude of square root, of, and these should have inner product, inner product notation. Inner product of B with itself. So that'll be 1, 1, 2, negative 2. 1, 1, 2, negative 2. All right, I think we've got it all cleaned up here. So here we go. This one will be the square root of 1 times 1 plus 2 times 1, 2 times 2, plus 4 times 4, plus negative 3 times negative 3. That's got to be less than or equal to the square root of 0 times 0 plus 1 times 1 plus 2 times 2 plus negative 1 times negative 1. And then this one will be, it's down here, plus the square root of 1 times 1 plus 1 times 1 plus 2 times 2 plus negative 2 times negative 2. So let's see what we get. So we've got 1 plus 4 is 5, plus 16 is 21, plus 9 is 30. So on the left side we have root 30, and that needs to be less than or equal to 0 plus 1 is 1, plus 4 is 5, plus 1 is 6. So this is root 6, and then 1 plus 1 is 2, plus 4 is 6, plus 4 is 10. Okay, so if we get decimal equivalents for these, on the left side it's approximately 5.48. On the right side it's approximately 5.61. So it checks out. Cool, cool? All right. Definition of orthogonal projection. So here, U and V are any vectors in an inner product space V such that V is not equal to the 0 vector. If that's so, then the orthogonal projection of U onto V is the projection of U on orthogonal projection of U onto V equals. So this is how. Now, how I remember this is that the vector that's doing the projecting is the bigger one, and the subscript is the one that's being projected on. Okay? All right, so this is the orthogonal projection of U onto V equals the inner product of U and V over the inner product of V and itself times V. This is super important. We're going to use this in the next lesson, which goes over the Gram-Schmidt method. All right? And so you'll be using this a lot. All right, so here we go. Orthogonal projection and distance. So this theorem says that the distance between U and the orthogonal projection of U onto V is less than the distance between U and some scalar times V, where C is not equal to the inner product of U and V divided by the inner product of V and V. Because if it was, it would equal to the orthogonal projection of U onto V. Okay? So, here we go. Consider the vectors. U is -1, -2, V is 4, 2. We're going to use the Euclidean inner product, the dot product, to find the following. Projection of U onto V. So, that's going to equal to what? The dot product of U and V divided by the dot product of V with itself times V, which equals, so what's the dot product? -4 plus -4, so we'll get -8 for the dot product of U and V. And then the dot product of V with itself is going to be 20. And then we've got the vector 4, 2. So this is going to be what? -2/5 times the vector 4, 2, which gives us the vector -8/5 and -4/5. Okay? Now let's take a look at the orthogonal projection of V onto U. So you'll still have the dot product of U and V, but now it's going to be divided by the dot product of U with itself times U. So we'll still get a -8 here. The dot product of U with itself is going to be 1 plus 4, which is 5. And then the vector U is -1, -2. So we'll end up with the vector 8/5 and 16/5. Groovy? All right. So, all right, why don't we look at a picture, right, of this stuff. And let's also look at a picture of the original vector so we could kind of scope it out here. So U, I'm doing pink, -1, -2. Let me extend this out a little bit. Okay, so U is -1, -2. And V is what? 4, 2. About here. Okay, so let's take a look. What do these orthogonal projections look like? So the orthogonal projection of V, actually U onto V we'll do first, this one here. And that was what? -8/5, -4/5. So -8/5 is about -1.6, right? And -4/5 would be about -0.8. And so, wow, look at that. That's the orthogonal projection of U onto V. Cool, cool? And do you see that it's on V. It's literally on V. Just going the other way. So we would expect that to happen for the orthogonal projection of V onto U. So let's see what we get. So for that one, let's do, we'll do this color here. So that would be this guy. So 8/5 is about what, 1.6? And then 3.2, 1.6, 3.2. So 1.6 and then 3.2, something like that. Okay, good enough. All right, so there you have it. You can get kind of a visual of what those projections look like. And next time we'll be looking at that Gram-Schmidt process. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Tell your friends. Bye.